Well, the Keeling curve records an effect on the atmosphere of human activity, a very profound one, in fact, because although carbon dioxide is a trace gas and its concentration in the air is quite low, it's capable of a very sensitive effect on the surface temperature of the Earth. In fact, it's not stretching it to call it Earth's thermostat. But once you think about this, you may well ask, as many people have, how is it possible that a single species of animal can have such a profound effect on the atmosphere and on the geophysical properties of the surface? Well, the answer lies in these enormous numbers. 1 billion tonnes in the climate game is called a gigaton, or a GT for short, and humans, just from burning fossil fuels, that's the biggest contribution we make, and making cement, put something like 38 gigatons of carbon dioxide into the air every year now. And if you add in the CO2 we make from ploughing up soils and cutting down and burning forests, and the methane from livestock and rice growing, and the CFCs and nitrous oxide from fertilizer and so on, and turn that into CO2 equivalent, the total is something like 43 gigatons. Huge numbers. It's very hard to get our heads around. Of course, the gases go straight into the thing we call the atmosphere. The atmosphere looks pretty impressive from down below where we are. All the weather happens there and it looks limitless, but of course once you see it from up above, it's not like that at all. The atmosphere is not much more than 20 miles high. You leave half of it behind at about 5.5 kilometers. At 32 kilometers, only 1% of it left. If you look at it from space, you can easily believe what is true, that the thickness of the atmosphere is like the thickness of a coat of varnish on a classroom globe. That's it there, that little ball. If you rolled all the gases up at surface pressure and put them into a sphere, they'd be about 1,400 kilometers in diameter. If you rolled the contents out of that ball, examine them, you find they're nearly all nitrogen, oxygen with a little bit of argon. If you're looking for the trace gases, including carbon dioxide, you have to look at that tiny red sliver at the top. Carbon dioxide, turns out, is about 1 molecule in every 2,500 of the whole atmosphere. And if you could put all the CO2 in the air into a box, a cubic-shaped box, before James Watt invented the steam engine, it would fit in a box about 100 kilometers on a side. This is how much we've added since then. Not all of it stayed in the air. Some goes in the ocean, some's taken up by plants, some goes other places. But this is a truly enormous change in the chemistry of the atmosphere that we've caused. If you put the modern quantity of carbon dioxide in a box, this is what it looks like. That's the part that existed before Industrial Revolution. This is the part we've added that's retained in the atmosphere. So just to help us get a handle on these very, very large numbers, here's a few little assistance for your imagination. This is what a box 1,000 tons of CO2 would look like at atmospheric pressure. This is what 1 million tons would look like. It's a bit less than twice the height of the Empire State Building with its spire. And to imagine a box big enough for a gigaton, you'd have to think of Mount Everest, but imagine its base at sea level. Everest is 8.8 kilometers high at its summit. So the box would reach up not far from the summit of Everest, and it would cover almost the whole of my home city of Ipswich if it was sat on top of it. Now here's the quite astonishing thing. We add one of those boxfuls of CO2 every 8.5 days, day in, day out, week in, week out. Now many people have said that even so, The flows of carbon into the atmosphere caused by humans are very small compared with natural flows, and that is true. But it doesn't actually help our problem. The problem is this. Although the carbon cycles on Earth's surface are very active and large quantities change places, from atmosphere to biosphere to soil to ocean and back again, the fossil carbon is foreign. It's been buried for tens of millions of years. It doesn't belong in those systems, and it's never been a balanced feature of them. So adding even the quantities that we do has seriously unbalanced the carbon cycle in such a way that natural processes won't be able to repair this for something of the order of 100,000 years. And of course, in the meantime, while it resides in the atmosphere, it acts as a powerful greenhouse, forcing on the surface temperature.